one more interesting series that you might come across is this idea of an alternating series. So what ends up happening, and this actually happens a lot in physical systems, is they kind of go back and forth between different phases. So you'll have kind of a positive state and a negative state, and a positive state and a negative state. And what you might want to figure out is that if I keep adding some value and then subtracting, and then adding and subtracting and adding and subtracting, how can I be sure that that's gonna stabilize, right? Because if I keep adding some numbers but I keep subtracting some numbers, is that going to kind of go out crazy, or is it going to somehow converge down to a certain value? And what we find is a nice technique to figure that out. So if I've got some sort of positive sequence, and I know that that positive sequence is non-increasing, so basically what that means is that it's either going down or staying the same at each term. So it might plateau and then go down and plateau and go down. And then the limit of that sequence is 0. And that's an important one. If those three pieces are satisfied, then if we have that alternating piece on there, that little -1, then oops, that needs laying in there. Those also converge. So that's kind of an important piece, because what it says is, okay, I've got some sort of thing that changes every time. Because like when n equals 1, that's a -1. When n equals 2, that's -1 times -1, so it's positive. When n equals 3, that's -1 cubed, so it's negative again. So this is a nice little way to model behavior of systems that sort of flip parity every term. It's not that this just came out of nowhere. This was a nice way somebody figured out how to represent behavior that was already happening. So anyway, this tells us, oh, if I've got some sort of sequence, that's how that converges. This is a pretty, I couldn't figure out a better way to represent this. I apologize. But if you look at these blue dots, this blue dots is the sequence. It's clearly going down. It's clearly going to 0. It's smooth sailing. The red dots are this -1 to the n plus 1. So it starts at an, but in the second term it goes down. It's negative. In the third term it's the same as the positive term. But then it's negative, positive, negative, positive, negative, positive, negative. And so what you're seeing when that happens is that you get a big addition to the series, but then I reduce it a little bit. But then I add more to it. But what I added to it is less than what I subtracted from it. That's a really important point here. What I added is less than what I subtracted. So you get back some, but you don't never get back to this point. And then in this one, when I subtract, but I subtract less than I added. So you never actually get back down to that point, and so on and so forth. So you have a situation where you keep adding, but what you're adding is a little, you're messing with it a little less. So each time it's less, the disturbance, that kind of harmonic behavior settles out, it bottoms out. So you have that, it dribbles into convergence. And we'll talk a little bit about this error piece in just a second, because we'll want to examine a really good case for this. So the harmonic series is a well-known divergence series, right? We've looked at it. It's we have P series to evaluate that. We can do the integral test to evaluate that. It is always divergent, right? But if I add this little -1 to the n plus 1, let's look at the terms of that. When I look at the first term, I get 1 plus 1. So that's -1 squared times 1 equal to 1. Okay. When n is 2, that's 2 plus 1. So that's 3. -1 cubed. And again, n is 2, so it's 1/2. So I have a -1/2. And then I keep going and get a positive 1/3, a -1/4, and a positive 1/5. Feel free to pause or whatever if you need to kind of walk yourself through that. Which means that if I take my partial sums, I start at 1, but then I subtract a half. So I'm down to 1/2. And then I add a third, so I'm up to 5/6. And then I subtract a fourth, so I'm down to 7/12. But then I add a fifth, so I'm back up to 47/60. So if you kind of look at what's happening here, I start at 1, I go to half, I go to almost 1 again, but I never get back up to here. But then I come down. But I didn't come down down to a half, I only came down to 7/12. Then I go back up, but I still don't go back up as far as this one. So I'm kind of stabilizing Because if I'm messing with it a decreasing amount each time because the sequence is decreasing, then I can only move within a certain window. And that wiggle room's got to stop. But I know that it's moving up and down, but that boundary is decreasing every time. So if that boundary is decreasing, I can't go anywhere. It's going to have to converge. But you might ask yourself, okay, that's great. It converges. What does it converge to? Well, there's no direct way to figure that out. But what there is an approximation. And that's, in practice, just as good. So what you might say to yourself is, okay, I'm going to generate 1 million terms. Is that enough? Do I need 10 million? Do I need a billion? Because obviously I can't generate an infinite number of terms. So if it's an alternating series, we have a really neat theorem. It says, look, if this thing converges, because it could still diverge, even if it's an alternating series, if it doesn't satisfy those three properties, then that error, or remainder, depending on what you read, the error remainder between the nth partial sum and the actual sum, then we have this bound. It says, look, the error between my approximation and the reality is less than or equal to the n plus 1th term. And that makes sense because, again, you're moving down and that bound is moving. Like I said, you can only come up so far. You always come up less than, or you go down less than you were before. So that's actually bounded by that term. And this is a result of actually like the telescoping series kind of stuff. And don't worry about that. But why is this important? Well, it's important because it says, look, if I want to know, I've got 47/60ths. Is that close enough? Well, if I take this remainder, it's the difference here, which is bounded above by the 5 plus 1. So really the 6th term, the next term in the list, which is 1/6. So if you say to yourself, well, I only care if I'm within 1/6 of the answer. Okay, then you can stop. But you may want more, so you may say, well, what happens if I generate 10,000 terms for this sequence? Well, based upon this, it's going to be less than or equal to 1/10,001. Now, again, this is only true because that's the actual sequence. If it was like 1/n squared, which we already know is convergent anyway, but if it was some other sequence that was alternating like that, then you'd have to use the actual sequence to bound it there. Why is this useful? Well, there's a couple things. You should always be doing this. This happens already when you do the nth term test for divergence, because you would test this already. And if this alternating term goes to 0, then the regular term goes to 0. So you're already doing the nth term test for divergence, hopefully, when you're starting with the series. So then you have to just check these two cases. Well, hopefully this is easy to figure out. Whatever you have, you just factor out a -1 to a power. Just factor that out. Whatever's left over, is it always positive? If it's always positive, that's pretty easy to see. This one can be a little more difficult. Clearly in this kind of case it is, because as n gets bigger, that's just, But you can plot it out, or you can maybe even represent it like as a function, take a derivative and figure out, is the derivative always decreasing? Well, if that's true, or is it the derivative's always negative, then if the function's always decreasing, the sequence is always decreasing. You have a lot of options here. But testing for alternating series is relatively straightforward, so it's one of the reasons that we really like to get things in this form, because we can get our answers super quick.